So now that we've learned how to take derivatives, we're kind of in our applications of derivatives mode. We started a few at the end of chapter 2. Chapter 3 is still devoted to applications of derivatives, and most importantly, what you cover in chapter 3 is graphing. So we want to be able, by the end of chapter 3, to take any function, a trig function, a polynomial function, a rational function, a root function, any function, and get a very detailed graph, including where its maximum value is, where its minimum value is, where it changes shapes from concave up, from bowing upward to bowing downward. So what we're going to do in chapter 3 is kind of go through how to find maximums and minimums, and how to talk about the shape of a graph as far as whether it bows upward or bows downward. Hopefully we'll cover most of this by the test time. If not, then not. I think the last section in chapter 3 has nothing to do with graphing. I think it's about optimization. So we only go up to 3.7. So 3.1 through 3.6 are about graphing in some way or another. Although we already did 3.5, okay? We covered 3.5 in chapter 1. That was about horizontal lines. I'll talk a little bit about it again, but we already covered 3.5. Had nothing to do with derivatives, it's all limits. And then 3.7 is about optimization, which is more work. So what I would like to be able to do is get through 3.6 before the test. So by the end of next week, I'd like to get through 3.6. If we don't, we don't. But that way you can, I can put some cool graphing problems on your test. Otherwise, whatever. Doesn't matter. Get as far as we can get. I'm going to just start with 3.1. Work our way through. 3.1 is about extrema. Specifically, it covers extrema on an interval, okay, because in the other sections, we do it not on an interval, extrema on a given interval. So I have to give you two definitions. These are not exactly the same as the book definitions, and that's okay because the book definitions are a little intense. But I need you to know what we're talking about.
Yes, please.
So extrema, I'll talk about what this word means in a second, but before that, let me give you the definition of an absolute maximum. Remember, in this chapter, we're gearing pretty much everything towards trying to get a good graph of a function. Right? And one important sort of point on a graph is what we call the absolute maximum. Right? So the absolute maximum of a function, absolute maximum value of a function, is the function value that is greater than all other function values in the domain of the function. Actually, I guess that's another question. So the absolute maximum is the greatest possible value a function can attain. This should be thought of, sort of compared to, contrasted with, a relative maximum. Now I'll give you some examples after I write this definition. A relative maximum value of a function is a function value so it's all the same so far, right? Is a function value that is greater than, now here's where it changes. Instead of being greater than all other function values, it has to be greater than all nearby function values. Where nearby is kind of a weak, mathematically ambiguous term that I'm using to save us ugly math notation. So the absolute max, or the relative maximum value of a function is a function value that is greater than all nearby function values. Kind of describe what nearby means in some examples. And you could do these definitions for minimum as well. Right, what do you think an absolute minimum value would be? What changes in the definition if I put minimum instead of maximum?
Less.
Function value that is less than all other functions. A relative minimum value is a function of a function is a function value that is less than all nearby functions. Okay, so it's the same idea for example. So here's an example. I'll draw you a function. Perfectly good function. Say it reaches up at, goes up to 1, 2, 3. What would the absolute maximum value of this function be? 3. The absolute maximum value of a function is the function value that is greater than all other function values. So the function value here that's greater than all other function values is 3. So absolute max value. What about relative max? Is there a relative maximum here? Yeah, so kind of the difference here, the absolute maximum value of 3 is bigger than all other function values. So therefore it has to be bigger than all the nearby function values as well. So an absolute max is always a relative max. So nearby means if you take this point and you focus on just an interval, an open interval really small around that point, on that open interval your 3y value is still the highest. Now,
You said it's always?
oh, absolute maximum has to be a relative maximum, yeah. If it's greater than everything, it's greater than everything nearby. Now, there might be other relative maxes, but this will always be a relative max. In this case, it's the only relative maximum. Right? If I pick another y value, say I wanted to make the claim that at y equals 1, for y equals 1, that's a relative maximum value. Can I say this is a relative maximum value? Why not? If you focus on a little interval, right, focus on this part here. There are points that have bigger y values on that little interval. So this is not a relative maximum. In general, you want to think of a relative maximum as the peak of a mountain, okay, and a relative minimum as the bottom of a valley. Now, I'll give you another example in a second. Kind of a convention that this book seems to use, if they ask you to find the absolute maximum, they actually want a point. Okay, notice I wrote absolute maximum value. Absolute maximum value is the y value. But if they say find the absolute maximum,
0, 3.
I would, just to be safe, I would put the point 0.
we put 0 and 3? I'm sorry. Absolute maximum. Why did we include the 0?
So you,
Is that what it happens?
yeah, that's the point that this is 0, 3.
So the, okay, I get it. The coordinates. Okay.
If I ask you for the absolute maximum, I'm looking for a point. That's all I'm saying. An absolute maximum value is technically a y value, but if I ask you for the absolute maximum, or if the book asks you for the absolute maximum, go ahead and give me a point.
It's a point.
So what about this guy? Let's see, this is 1, 2, 3, 4. -1, -2. This is up at 3, this is down at -4. First question, do I have an absolute maximum or an absolute minimum?
Okay. You have no solid number.
Right, so there's no, an absolute maximum is a function value. So the function doesn't actually ever get to infinity. Right? It goes on forever, but it doesn't actually ever get there. So you don't have an absolute maximum or absolute minimum. Because no matter which point you pick on this function, I can find you a higher point. That's what this arrow means. And no matter which point you pick on the function, I can find you a lower point. That's what this arrow means. So there is no absolute max or min. What about relative? So relative max means you have to have a y value that's higher than all the nearby y values. So if you look at this point, at the top of this mountain, and you look at the nearby function values, they're all going down. So this would be a relative max. If you look at this point down here, and you look at all the nearby y values, they're all going up. So this would be a relative min. The relative max is, say, -2, 3. Relative min, 4, -4. What would I have to do? I won't do it. But what would I have to change in this picture to turn this relative max into an absolute max?
Make that one curve back down.
Yeah, I could make this curve back down, but I'd also have to make it curve back down before 3.
Less than.
So one way to do it would be if I change the picture like this. That would add another relative max, right? Well, another way to do it is to just stop the function. Done. But so my point is, because there's an arrow going up, that's what's stopping this from being an absolute max. What do we do? Ooh. So what about silly function? Not a silly function. What do we function? 1, 2, 3. Solid dot, line. I want to know about the absolute max, absolute min, relative max, relative. Talk to me about absolute first. What's the absolute highest value this guy attains? 3. So this guy right here is an absolute max because you never go any higher. This guy right here is an absolute min because you never go any lower. So the absolute max 0, 3, because that's this point. Absolute min is equal to -2. And even though it It doesn't come up so often that you're asked for relative max and min on a closed interval when you have these solid dots. But technically, by the definition, this would also be a relative max because it's higher than all the nearby y. This would also be a relative max. If you compare it to all the nearby function values, this is the smallest. So I'm going to take out these points on the end. The thing that I want to call my absolute max, I'm going to take it out. The thing that I want to call my absolute min, I'm going to take it out. But I'm going to draw a segment between. So open circles on both ends. Talking about absolute max, absolute min, relative max, relative min.
What is the question?
What is the absolute max of this function?
Is it related to limits at all? No.
It doesn't exist.
Hmm?
Doesn't exist.
Yeah, there are none. No absolute max, no absolute min. No absolute max. Min. No relative max. Why not? The only point that you could even consider to be the relative max would be at 0, 3. But it's gone.
What about
Right?
before?
Any other point you pick. Right? And you can't go just before 0 on the x-axis. Right? If you go to negative 0.1, I can find a point that's higher on the x-axis, right? You go over
Okay,
here.
there's no easily.
No, there's no
No.
point, right? The way this works is no matter which x value you pick here, I can find one that's closer, and so I'll have a higher point.
If you keep adding digits after this.
Yeah, but you have to stop somewhere. And once you stop, then I will have one less or something to get closer. No matter how close you get to 0, no matter which point you pick, I can find a point that's higher. So there is no relative or absolute max. Same thing over here. No matter which point you pick down here, I can find a point that's lower.
What if I have a circle and then like going like this and then an arrow at the end?
Yeah. So if you have other mountains and peaks and valleys in your graph, then those will be max and min. So if you have like circle, open circle over here, then you come down and then you go back up like this, something like that. Is that what you're talking about?
My circle I meant I don't have like a min to make it doesn't exist. Like make the curve back down and the circle is below the, yeah, and then the circle there. Circle there instead of an arrow. Yeah.
But a point here.
No, that's continuous.
So a point. So like
Yeah,
this.
it's continuous, yeah.
Gotcha.
Where the circle is below the curve.
Yeah.
So then I still don't have a min, right?
No. So, depending on whether or not this goes lower than this, you might have an absolute min or not. So let's say, do you want this to go lower than this or
Lower,
not?
yes, that's the case. Because if it wasn't, there is no need to worry about it. We'll just use the...
Well, so if this goes lower, then there would be no absolute minimum. Would there be an absolute maximum?
We'll use the...
No, there'll be no absolute maximum because this guy's an arrow. He keeps going forever.
Okay.
So there will be no absolute min or max, but relative you will have. Right, this guy here will be a relative max, whatever point this is, because it's higher than all the nearby points. And this guy here will be a relative min, because it's lower than all the nearby points.
Okay.
But you can't have absolute because no matter which y value you think is the smallest, I can find a point that has a smaller y value. I'm gonna jerk like that. So these ones with the open circles are kind of tricky. We don't talk about them that much. What about, oh, by the way, I'll give you one more. So typical example, right, parabola, like that. But I take out this point on the top here, and I stick it down here instead. So absolute max, absolute min, relative max, relative min. So certainly no absolute min because you go around forever, and no relative min because there's no valleys. Now, well, maybe a relative min. Let's talk about that. Certainly no absolute min. What about absolute max? So can you point to a highest value that this function attains?
That one solid point.
No, that's
Well, this is not the highest value because this guy's higher.
Yeah.
So there's no absolute max. Now, relative max would be a point that's higher than all nearby points. Now, as far as nearby goes, you think of nearby as an interval on the x-axis. So for example, if you wanted to call this guy a relative max, then you would have to look at points that have nearby x values. So you'd be talking about these points up here. So this guy is not a relative max because he's not higher than all the nearby points.
Mm-hmm.
He's actually a relative min.
How come?
Because it's lower than all the nearby points. Nearby being defined on the x-axis here. These are the nearby points.
Okay.
So this point is not a relative max. This point is a relative min because it's lower than all of the nearby function values. What if I took this point out altogether?
I don't have one.
Would there be another relative min somewhere else?
No.
No. Then there's nothing. All right, what if I took this point out and I put it up here? It become a relative max because it's higher than all the nearby points. So an extremum is a maximum or minimum. Extremum is just a word that encompasses both the words maximum and minimum. If I want a relative max or a relative min, then I will say find all relative extreme. And the plural of extremum, by the way, is extrema. And the plural of the book uses for maximum is maxima. Two of these would be two maxima. Just so we don't get in language. Just keep here. So if I want to know all the relative maxes and relative mins of a function, I will say find all relative extremes. If I want to know all the absolute maxes and absolute mins of a function, I will say find all absolute extremes. So this word encompasses these two. I'm done with calculus here. Ooh, calculus. Sweet. First derivative theorem. to motivate a new term I'm going to define in a second. But the first derivative theorem, which hopefully will make some sense, says that if f, the function f, has a relative extrema at x equals c, then f prime of c equals 0, or f prime of c is undefined. So if you have a function that has a peak or a valley, right, a point that's higher than all points nearby or a point that's lower than all points nearby, notice I use relative, so we're only talking about nearby. So if f has a relative extrema at x equals c, then the derivative at c is either 0 or undefined. So let's think of a couple ways that, let's just take maximum for example. Let's see if this makes sense. So what are a couple of ways you can have a maximum? So the typical way would be like an upside down parabola, right? If you have the top of a mountain. This guy's a relative maximum. Relative max. And the claim here is if this occurs at C, then f prime of C is 0 or undefined. What's f prime of C in this case? 0. Because if you look at the tangent line, m equals 0. So in this, so one thing this is saying is, if you have a relative maximum, one possible option is you have a horizontal tangent line. Horizontal tangent line. Right? You need slope 0. What if you had a horizontal line? A horizontal line doesn't have any relative maximum technically, because relative maxima has to be higher than all the points around it, and all the points are equal to the horizontal line. Yeah, so you do have to be careful. This is not saying if the derivative is 0, then you have an extrema. It's going the other way. If you have an extrema, then the derivative is 0. But what's the other? What are other ways I can have a relative maximum without being? I don't know. Well, how else can I get a relative max? What other picture can you think of? Yeah, so another way would be like an upside down absolute value. That would work. So this is your x equals c. So this, an upside down bird shape, will be the same situation. So what's the slope, or what's the derivative here at x equals c? Undefined. So this is the case where you have derivative undefined. Right, because all the secant lines have slope 1 on this side, or positive 1, and all the secant lines have slope negative 1 or something on this side. Right, so there's a jump as far as slopes go, positive to negative. F prime's undefined. A bird would work as well, where you have another sharp point. So can you think of something that's not a nice round edge and not a sharp point, where you have a relative maximum? So pretty much the only other options are discontinuities. Okay, so for example, we had this one just a second ago. Open circle here. Put that point up here. So this point would be a relative maximum, but your derivative would still be undefined here, because if your function is not continuous, your derivative is not defined. So, if you know you have a relative maximum or minimum, right, relative extrema, then you can say at that point your derivative is either 0 or undefined. You either have a nice function and your derivative is 0, or you have a not so nice function and your derivative is undefined. What this leads to is talking about something called a critical number. Super important when we start graphing. The critical numbers of a function x equals c is called a critical number of a function f if f prime of c equals 0 or f prime of c is undefined. So all the places where your derivative is 0 or undefined are called critical numbers, because something interesting happens. The assumption is that c is actually, this c has to be in the domain of f. So x equals c in the domain of f. Meaning that if you get a critical number, if you get an answer for a critical number that's not in the domain of f, you don't even care because it doesn't make any sense in the original function. So let me do some critical number examples. Find all critical numbers. Oh, what have I got for you? 6x squared minus x cubed. That's the first function. Yeah, so critical numbers come from where the derivative is either 0 or undefined. So if you want to find critical numbers for any function, your first step, take the derivative, right? So f prime of x is equal to what here?
12x minus 3x.
16. 12x minus 3x squared, right? The 2 comes down. With a 1 exponent left over, the 3 comes down, with a 2 exponent left over. So this is f prime of x. If you're finding critical numbers, you care about two things. You care about where the derivative is 0 and where the derivative is undefined. So you always have to consider both of these. Usually this leads to most of your solutions. So you take your derivative and set it equal to 0 to find your critical numbers. What are we going to get here?
0, 4.
Yeah, so you can factor. I'll factor out of 3x, leaving me with 4 minus x. So the places where my derivative is 0 is that x equals 0 and x equals 4. So these are definitely two critical numbers. What about over here?
No.
Is this derivative ever undefined? Is there any place you can run into problems when you're plugging in x values? No. For undefined, you really want to focus on denominators, okay, and roots. But if you don't have any denominators or roots, then you're never undefined. So this doesn't lead to any extra solution. So these are your two critical numbers for this function. Now, that doesn't actually necessarily mean that these two values tell you where you have a relative max or not. Okay, the theorem we talked about before goes the other way. If you have a relative max, then you know that's a critical number. But if you have a critical number, you don't necessarily know whether it's a relative max, relative min, or anything. So in section 3.3, we talk about how to figure out whether these give you relative mins or maxes or what they mean. Right now, we're just finding the critical numbers. Pretty straightforward. Be careful. Since we're setting the derivative equal to 0 now, you guys are going to get in the habit of setting the derivative equal to 0, and you're going to do it when you don't need to, and I'm going to mark you off. All right, so the only time you want to set the derivative equal to 0 is if you're trying to find critical numbers, or trying to find like horizontal tangent lines. So don't just start setting derivatives equal to 0 because you feel like it. Because you're bored with the problem that I asked. Make up your own problem. Let me show you the question you should have asked. So what about this guy? G of x is equal to the square root of 2x minus x squared. I want to find the critical numbers. So to find critical numbers, you need to know the derivative is 0 or undefined. So you got to find the derivative first. G prime of x is equal to, I would probably rewrite this with a 1/2 power to make it a little easier to derive. 2x minus x squared to the 1/2. So then what happens when I do my derivative here?
Put a half.
1/2 times 2x minus x squared to the
Negative half.
negative 1/2. Done?
No.
Go, chain rule. Absolutely chain rule. Times the derivative of the inside.
2 minus 2x.
2 minus 2x. So let me clean this up a little bit.
Yeah, please.
Especially since I want to know where it's undefined at 0, it'll help to write it as a fraction. So this guy goes in the bottom since it's a negative exponent, and there's a 2 in the bottom as well. So I'm going to write, oh actually I could reduce, but let me get there in a second. So let me bring this down to the bottom. Square root of 2x minus x squared. This guy stays on top. And if you wanted to, you could, if you wanted to reduce this, you could factor out a 2 on top, right? It's not super necessary. This would be 1 minus x, and you factor out a 2, and then these 2. So 1 minus x over root 2x minus x squared is my derivative. How do I find critical numbers? Yeah, so critical numbers are when your function is 0 or undefined. Function being 0 is the same thing as saying the numerator is 0. Function being undefined in this case is the same thing as saying that your denominator is 0.
Or negative.
Or, well, okay, so now, yeah. Why do I not care whether my denominator has a negative in the square root? Right, because if I'm talking about, remember, critical numbers come from where g prime of x equals 0, or from where g prime is undefined. Right? And for g prime of x equals 0, like we said, that's straightforward. You just set the numerator to 0. One minus x equals 0, which gives you x equals 1. That is absolutely a critical number. Now over here, for the derivative to be undefined, technically I have two things to worry about.
Bottom half too.
I either have where the denominator is 0, or I have where when I get a negative under the square root. So this case was the numerator 0. Now I need to worry about the denominator 0. Which would be when root 2x minus x squared equals 0.
Which is x equal 2.
And the root isn't really doing much since it's equal to 0, because you can square both sides. So this will become 2x minus x squared equals 0. And then if you factor, pull an x out in front, this will be 2 minus x. So what x values do I get here? 0 and 2. From each of these. When x is 0, the denominator is 0, and when x is 2, the denominator is 0. Now I come to the technicality. Technically, I should worry about when 2x minus x squared is less than 0. Because if I get a negative underneath my square root, my function is not defined. My derivative is not defined. But I'm not going to worry about this because my original function would be undefined there. So I'm not going to get any critical numbers from this because there's no function there to begin with. Does that make sense?
Mm-hmm.
This is a domain restriction here. You can't have 2x minus x squared less than 0. So you cannot have, as soon as you write this function down, 2x minus x squared less than 0. Or else the function's undefined. Which means this portion of the critical numbers is not part of our function. So these are not technically critical numbers. These are not in the domain of the function. Are these in the domain of the function? 1, 0, and 2?
Yeah.
You could check, right? If you put 1 in here, 2 minus 1 is 1, root 1 is fine. If you put 0 in here, 0 minus 0, that's fine. If you put 2 in here, 4 minus 4, that's fine. So these are all okay for the original function, but these two come from where the derivative is undefined, and the original function is still okay, still defined. You guys can solve this anyway. I don't have any faith. I don't have any faith that you guys can figure out the solution to interval for this. But maybe you'll do it and prove me wrong.
No, you're right.
Yeah. Luckily, we don't need to. Questions?
They're like praying, please don't let it be. Questions?
So undefined, we're going to set denominators to 0, and then when you're trying to find what the derivative is 0, you set the numerator to 0. We do one more. You need, got to have a trig function, right? Absolutely. Absolutely. We're super pumped about this trig function. H of x equals sine of 3x. Find all critical numbers. All places where the derivative is 0 or undefined. So first we've got to find the derivative. H prime of x equals derivative of sine is cosine. But chain rule tells me to multiply by the derivative of the inside, right? We have an inside and an outside. So we do the derivative of the outside, which is cosine, keep the 3x the same, then multiply by the derivative of the inside. So let me put 3 up. Now, in the great scheme of things, for this particular question, this 3 doesn't matter, but it should still be there. I have two places where I get critical numbers, where the derivative is 0, or where the derivative is undefined. is cosine ever undefined? No, cosine's this nice, happy wave, right? It's never hurt anybody. So this doesn't give us any solutions. But we can set it equal to 0. I just taught my trig class how to do this today. So let's see if you guys can remember. I have to set 3 cos 3x equal to 0. That's all for x. Yeah, so, well, okay, so one thing, first of all, this 3 on the outside is useless, right? This doesn't do anything. Since it's equal to 0, I can divide that out right away. So I just need to solve where cos 3x equals 0. But I need to find all the places where cos 3x equals 0. I don't know. There's a couple ways to do this, but you guys tell me what do you know? You could graph it. It's a lot of work. It's a lot. I mean, it'll work. It'll get you there, and I'm super okay with it.
Find where cosine of x equals 0.
Yeah, so first just tell me where cosine equals 0. All right? So just think about for a second where cos theta equals 0. Forget about the 3x. Where is cosine of theta equals 0? So on your unit circle, cosine is equal to 0 when your x value is 0. So either here or here. But I want all places where cosine 0 because I'm trying to find all critical numbers.
Plus pi.
Plus 2 pi.
So if you start at pi over 2, how much do you have to add to get to your next critical number?
Pi.
Pi, and then or your next 0, I'm sorry. And then you have to add pi again, and then add pi again. So all solutions to this would be
Plus k pi.
theta equals pi over 2 plus n pi. Because either you're here, or you go pi, and then you're here, or you go pi again, etc., etc. So that's all solutions to cos theta equals 0, but I don't care about theta, I care about x. So what I really want to know is where is 3x equal to pi over 2 plus n pi. Now to solve this, right, this theta and 3x are the same thing in my problem. So I can set 3x equal to this. And then I multiply by 1. Because that will cancel out my 3. So this guy will be pi over 6. X equals pi over 6 plus
X over 3. X pi over 3. N pi.
n pi over 3. This is all critical numbers. Right, so for any integer, any whole number, positive or negative, you can plug in there and you'll get a critical number. Remember that at all? No. Yes.
That was similar to that question on exam.
What's that? Question?
That was similar to the question on exam 1.
Yes. So the question on exam 1 talking about the where tangent is continuous. Yeah. Okay, cool. That brings us to kind of the point of this section. So we know how to find critical numbers. But now I want to find absolute extrema So I want to be able to take a function and find the absolute extrema. Normally this will be on a closed interval. Well, not always. So So the idea is if I give you a function, you need to somehow be able to narrow down where the possible absolute extrema are, and then test those points and figure out which ones are the absolute, which point is the absolute max and which point is the absolute min. So here's kind of a picture. So suppose I have a closed interval, for example, from A to B. My function comes up, and it looks like down, stops right here at B. So my question is, how would you go if you had a formula for this function? What are sort of the suspects that you would look at for absolute max and absolute min? Like, I'm not going to say this is from -1 to 2. I'm not going to have to plug in every possible x value, right? Because some of these are obviously not absolute extreme. Right? Like this point here is obviously not an absolute extreme. It never will be because it's going down on one side and going up on the other. But there are kind of usual suspects that you're always going to pick on. This guy, and any of these guys can be absolute extreme depending on the function. So sort of the strategy to narrow down your search when you're given a function, when you're given a formula for a function, you're looking for an absolute extreme value. To narrow down your search, you're only going to focus on the endpoints, if you're on an interval, the endpoints, and then any places where you could possibly have a relative max or a relative min. How do you find the places where you could possibly have a relative max or a relative min?
When it curves.
When the derivative is 0 or undefined. Okay, so sort of the strategy here to find absolute extrema first, you narrow down your search by finding all critical numbers. And then into the function, into the original function, you plug your critical numbers and your endpoints of the interval, if you have them, and you test, you figure out which one's actually the highest y value, and which one's actually the lowest y value. So we'll plug critical numbers and any endpoints of the interval into original function. The place where you have the highest y value, right, the highest result of this test of plugging in the critical numbers and the endpoints is your absolute max. Lowest result, lowest y value is your absolute. Find out absolute extrema on a given interval. So suppose I gave you the function 2x cubed minus 6x, but I only care about this function on the interval 0 to 3. absolute maximum value and my absolute maximum point and my absolute minimum point. The idea is the only place this guy can have an absolute max or min is at one of the endpoints or where it turns around. So I'm going to find all the critical numbers first and then test those against the endpoints and find the highest and the lowest. How do I find critical numbers? Derivative equals 0, right? So find critical numbers. So first I find f prime of x, which is equal to what? 3 comes down, so 6x squared. Now critical numbers happen when the derivative is 0 or undefined. Is the derivative ever undefined here?
No.
No, it's perfect. There's no denominators, there's no roots, there's no problems. So this guy doesn't help me. But f prime x equal to 0 will tell me a couple critical numbers. So I'll set 6x squared minus 6 equals 0. Add the 6. 6x squared equals 6.
So 1 or negative 1?
Divide by 6. X squared equals 1. Yeah, you got to be careful when you square root both sides, you get 2 solutions, right? Yeah. So at the end here, when you finally do your square root, don't forget to do plus or minus. X equals plus or minus 1. So those are my critical numbers. Step 2 is to test. So I'm going to take x values and find the corresponding f of x values. What I test is both my interval and my critical numbers. So I have to test -1, 1, 0, and 3 into my original function. So let's do the interval. Let's do the interval first. So if you plug in 0 to f, what do you get?
Negative. Oh,
0.
I thought I was working negative one side.
Ah, I tricked you.
Yeah.
If you plug in 0 for x, you get 0. What if you plug in 3?
2 times 27.
All we're going to do is subtract. Work your telling me fine. 2 times 27 minus 6 times 3. So 54 minus 18? 36?
Wait.
That seems pretty high. All right, 1 and -1. So if you plug in -1, -1 cubed is -1 again. So this will be -2.
It's not the interval though.
4.
Oh, it's not on the interval. What's that mean?
You don't care about it.
Doesn't matter. You can do it, right? You can plug in the -1. You would get 4, but it's irrelevant. Oh, no. These are the critical numbers, but if we're looking for extreme on this interval, the -1's useless. Good eye. What about 1?
Negative 4.
-4, right? Because 2 minus 6 will be -4. Okay? So the absolute maximum will be the highest y value, so it'll be here. So this point will be your absolute max. Your absolute minimum will be the lowest, the point that has the lowest y. And as of right now, we're not really sure what happens. So for your final answer, you put absolute min is at the point 1, -4. Absolute max is at the point 3, 36. So whatever this function looks like, I don't have a whole bunch of information about it. I know that it's at 0, 0, because I plugged in 0. I know that it's at 1, negative 4. And I know that it's at 3, 36. So we'll go 36, way up here. So at least on this closed interval, from 0 to 3, decent idea of what we're looking at here. How do I know, by the way, it didn't ask you to graph it, but I'm just kind of giving you an idea of what we've learned here. How do I know it doesn't turn around again? How do I know there's not a bunch of other humps in here? And so how do I know it doesn't go like hump and then another hump here and then up to 36? Because you'd have another critical number, right? That's the idea about critical number. At a relative min or max, you have a critical number. So in this case, I'd have two critical numbers, but I know my only critical numbers are at 1 and negative 1, so I can't have an extra one.
Very good.
How do I know it doesn't go higher than 36? How do I know my function isn't way up here at, I don't know, 54?
Because that's where the
Because that's where if like x equal 3, you get the 36.
So for example, if I did this, how do I know that doesn't happen?
It's not a critical number.
You have another critical number. Right? You have another critical number. Because that's relative math, so it would have a critical number. Okay. Questions before I move on? That's what I got for you. Glad I lost for you. I only have 10 minutes. I want to find the absolute extrema, so same instructions, but I want my function to be g of x equals cube root of x on the interval -8 to 8.
Rewrite it.
So yeah, if you're finding absolute extrema, you want to find critical numbers and then test those against the endpoints, but to find critical numbers, you need a derivative. So let's go ahead and write this as x to the 1/3. What's my derivative? So the 1/3 comes down, g prime of x equals 1/3 x to the negative 2/3. Or g prime of x equals 1 over 3 cube root of x squared, or squared on the inside if you want. So what are my critical numbers from here?
0.
So first set your derivative to 0. When is g prime of x equal to 0? Never, actually. Because in order to be 0, a fraction has to have the numerator 0. The numerator is always 1. So this is actually the useless one in this case. This doesn't lead me to any information. But my other situation is when g prime of x is undefined.
Which is x equals 0.
Yeah, so if x equals 0, this is going to be undefined. Now, is that a problem in the original?
No.
No, x equals 0 is okay.
Still positive.
So denominator equals 0. And that's going to leave you with x equals 0. So your only critical number here is x equals 0. Which is on the interval at least, so that's good. So that's your first. Find the critical number. test your critical numbers against your endpoints and see which one's the highest and which one's the lowest. So we have -8, 0, 8. -8 and 8 are coming from the endpoints, and 0 is coming from my critical. So,
-8 undefined.
so plug it into the original function. So when you put -8 in here, you get cube root of -8, which is -2.
Oh.
Right, what do you multiply by itself 3 times to get -8? -2. Cube root of 0, 0. Cube root of 8,
2.
okie doke. So what's my absolute max? Absolute max.
Min is -8 comes into 2.
Right, so it's the endpoints here. Here's your absolute min.
Mm-hmm.
Here's your absolute.
That's 6 number 2.
-8, -2. 8, 2 for the max. What happens at 0, 0? Do you guys have any idea? We actually know what the graph of this looks like, so you have some kind of idea. Well, maybe you know what the graph is.
Oh, it's vertical tangent line.
Yeah, so cube root of x is like x cubed but flipped on its side. Okay, so cube root of x looks like this. So here's -2, -8. Here's 2, 8. Absolute min, absolute max.
I still don't see how you.
So I have a vertical tangent line here, but I don't actually have any, not even any relative extreme, right? Because it's not a peak or valley.
It's the 8 negative.
Oh, I flipped the 8 too.
Oh.
Thank you. Yeah, so this would actually be 8, 2. If it were on x cubed, then it would be 2, 8, but it's on cube root, so 8, 2. Do one more. Do a trig function.
So the tangent line would be vertical.
Yeah, it's a vertical tangent line here. You can tell that it's a vertical tangent line here either by the graph, if you're really careful, or by the fact that your derivative is undefined. So your slope is undefined. Okay. Ooh. Ooh. I don't know which one you're going to like more. What's this? C. Are we on H? Secant x will be my function. On the interval, -π/6 to π/3. Secant x. I want to find absolute max, absolute min on the interval -π/6 to π/3.
The derivative.
So you gotta find your critical numbers. So let's go ahead and find the derivative. Right, that'll help us get the critical numbers. You know the derivative of secant is secant tangent, right? So my derivative is secant x tan x. Critical numbers are going to come from where this is 0 and where this is undefined. So we have to worry about h prime of x equal to 0 and h prime of x. So let's start here. In order for secant x tan x to equal 0,
Either secant equals 0 or tangent equals 0.
yeah, you said each one equals 0. Either secant x equals 0 or tangent x equals 0.
Or both.
I would probably think of these as fractions. Secant is 1 over cosine. So is 1 over cos x ever equal to 0? No, in order for a fraction to equal 0, the top has to equal 0. This gives us no extra solutions. For tangent, think of tangent as sine over cosine.
Squares, tangents.
So in order for tangent to be 0, sine has to be 0, where sine equals 0. It's 0. Well, there's lots of places. Right, in order for sine to be 0, you have to be at a y value of 0. So either here or here. So you're either going to be at 0 or pi or 2 pi or 3 pi or go backward and get negative pi.
Plus n pi.
Yeah, look at the interval though. The only one I really care about is going to be 0. Because pi is too big and negative pi is too small. So the only critical number on the interval that I care about would be x equals 0. Now if I didn't have an interval, or if I had a bigger interval, I might have to find more critical numbers or do plus n pi or something like that, not 0, which is n pi. But I do have an interval, so I'm not going to worry too much about it. What about where h prime of x is undefined? Will it be undefined? Yeah, sometimes the derivative will definitely be undefined. Right? Because the derivative is 1 over cosine times sine over cosine. So the derivative will be undefined whenever cos x is equal to 0. Why don't I care?
Because it's not in my intervals.
Yeah, lots of reasons. One, wherever this is 0, the original function is also undefined, so it wouldn't be in my domain no matter what.
Yeah.
Okay. Another way to look at it is cos x is equal to 0 for the first time at pi over 2. Is that in my interval? No, it's bigger than pi over 3. And it's equal to 0 down here at negative pi over 2, which is still out of my interval. So this actually doesn't contribute any solution either. So all I have to do is compare 0 to negative pi over 6 and pi over 3. So I do secant of negative pi over 6, which is 1 over cosine of negative pi over 6. Cosine of pi over 6?
Somebody.
2.
So pi over 6 cosine is root 3 over 2.
Oh.
So at negative pi over 6, cosine is even, so it'll be the same thing. So this ends up being 2 over root 3. Secant of 0, 1 over cosine of 0, 1 over 1, 1. Cosine of 0 is right here. Pi over 3 is up here, the 1/2 of the root 3 over 2 switch. So secant of pi over 3, 1 over cosine of pi over 3, so the reciprocal of 1/2. So what's your biggest, what's your smallest? 2 divided by a number bigger than 1, so this guy is smaller than this. And it's not, right, it's 2 divided by 2 would be 1, but it's divided by something smaller than
That's
2.
smaller than 2, so this guy's between these two.
That's square root of 2.
So it's
Right? If you thought, what's the decimal for 2 over root 3? 1 point what? Someone tell me the decimal for 2 over root 3. Nobody has a calculator?
1.73.
1 point what?
73.
So now it's an easy decision, right? Easy decision. We don't have to use any logic at all. Here's your absolute max. Here's your absolute